everyone. Currently, software engineer who has mostly worked into infra teams like core security team or observability team, and most recently into advertising space. Uh, and I decided to learn AI and machine learning. For me, the best way to learn is if I'm building something, and while building, I'll just learn all the concepts. So yeah, here I am, and I'm going to record whatever I learn, and hopefully it can be useful to other folks as well. But quick info about this video is I'm absolutely beginner into machine learning part. So if you're ML expert, this video isn't for you. And so for this video, I'm just going to use the simple tools that are available to me pretty easily. For example, this Google Colab that I'm going to use. It's almost like Jupyter Notebook. If you don't know Jupyter Notebook, it should be fine. And this Google Colab also provides GPUs that we can use. For the next part, I'll be turning off my video and we'll be building Spotify script predictor. It is basically a code that will look at the data from Spotify, and through machine learning, it will tell if the user will skip the song or listen to it. We'll deep dive more into how it will do it later in the part of the video. I'll tell you where the dataset is. Dataset is available into this GitHub, into the GitHub link. Probably someone has uploaded this dataset from Kaggle into GitHub. Normally, please don't upload huge files into Git because it causes like a permanent repository blot and destroy like performance for Git commands like git add or status or that kind of commands. But I think this file is probably smaller, so it should be okay. Next, we will be let's deep dive into the code. So let's start. Let's create a new file into Google Colab. Name it something like learning Spotify. Okay, yeah, learning Spotify skip, and then we'll click on connect. So when we click on connect, we are asking Google that hey, give us some host. So for example, here basically Google is giving us a temporary pre-configured like a Linux virtual machine environment. So if you click on this one, RAM and disk, you can see here if the system RAM is 12.7 GB and 1 GB is used, and disk space is 20.3 GB out of 108 GB. It means it's basically like Google can just give us like a blank slate here, or we can just create something new in our Visual Studio Code and start building it. But then we have to install all the drivers. Like if we are using GPU, we have to install GPU drivers, or we have to download this massive data science libraries like TensorFlow, or even like a small Python libraries like Pandas and NumPy for machine learning development. But here Google is just giving us all everything into like a ready host which has everything installed. For example, that's why the disk space is 20.3 GB here. And you can even change the runtime. You can connect to another runtime here as well. And you change runtime type. So how many types does Google provide is CPU and T4 GPU. It's basically NVIDIA's own GPU. And then you can change the runtime type like Python, or you can code in R and Julia, which I don't know what is Julia, but Python and R. Um, Here we keep going with CPU. GPU is when we have to do much better stuff. Like we have a lot of data to load, and we have to uh, train some complex models. But uh, let's just right now go with GCPU. And probably you can run all the same things in GPU as well. I have not tried it, but you can try. Okay, let's start. I'll first import pandas to read the CSV file. CSV file. Good. And we just call print fetching data from GitHub CSV file, something like that. And then we'll just call df equal to panda.read CSV. I'm going to give the URL. Next, we'll just do df dot pandas dot read CSV file, and then we'll just successfully read the file and we'll do the data preview. It will display df dot hide, and let's run it. Awesome. So what this is doing is what we did is we just imported pandas as PD and then we could the CSV file we gave it to pandas to read. What pandas is doing here, it's calling the GitHub and it's streaming all the data. Since this is a CSV file, we call read CSV. So pandas will stream data over internet and then store the whole file as a data frame in pandas. Pandas is a concept called data frame. And then we call data from that head, which will just show us the first 5 rows. You can see that our data contains columns like track name, track artist, and this all are text columns. Neural network cannot understand text, a string, or words. You'll understand that later in this video. But for now, you can assume that machine learning is simply addition, subtraction, and division of huge set of numbers. Before we dive deep into how to train the model, we need to see what to do with those columns that contain text, string, and this words values. There are total 4 standard ways that we can take care of those columns. We'll go through each way and apply it to our data. First one is one-hot encoding method. One-hot encoding is a method of converting text categories like into multiple yes and no columns so that machine learning model can understand them. For example, here we have a genre as a column. You can see there's a playlist genre. Let's see how many unique values exist in that column. Let's write yes. We'll just see from our last data frame. DF is the data frame that we created here. Dot and unique. Let me run both the things. Okay, that's finished. So here you can see we have 6 unique values. So there are like, for example, here we have a pop, we might have rock or any other romance, any other genres, a song genre. Now, if we want to convert this data into some numeric value, we can convert it into 6 columns. Each one will contain either 1 or 0 as a value. Let's see the code and you'll understand it more on it. Let me write it. Translating playlist genre into binary checkboxes as a column, right? Now we just create df encode it. We are creating a new data frame. We are telling pandas dot get dummies. We are giving it our previous data frame and we'll give the columns. Which column we want to convert? We want to convert playlist genre as a column, translating complete. And now we'll just print it. Again, display data frame dot head. We'll just get first 5 columns. And it did not get converted. Let me see what happened. Playlist genre. We are displaying the data frame, not data frame encoded. Because data frame encoded is the one that contains these different genres. And where are the genres? Yeah, yes. Here you can see uh that we have these different genres created, like playlist genre, Latin, playlist genre, pop, R&B, rap, and rock. These are the 6 genres that we found out previously we had. Let's look into the code. The get dummies function looks at the playlist genre column and finds all the unique genres and automatically builds a new checkbox column for each one. The original playlist genre column is gone. In its place, Pandas created a brand new columns. As we can see from the text column, got converted into several new checkboxes columns like true and false values. So for example, let's say if there was one song, for example, this Ed Sheeran song, I Don't Care with Justin Bieber. Here we can see that this column's genre was pop. So in that case, for all the 5 genres, all the 6 columns that we created, all of its values will be false, false, except the pop genre. So this column's value will be true, and all the other columns values will be false. So the same way, we have different. For example, we have a track name as a column. If we want to convert track name into checkboxes kind of column, this true and false values. Let's see how many unique checkboxes columns exist for us. Uh, Track name, uh, and let's use df encoded instead of data frame. We have 23,449. So that if we want to create for a track name the same way, it's going to create 23,000 columns. That's so much waste of our memory. That now we have a bunch of columns with all the columns will like after for every column, we will have like a one value as true. The other 23,448 values will be false. So there's so much waste of that data and waste of memory that we are doing. So this is useful when a small number of categories are there for you. Usually under like 10 or 15 of these different unique values are there in the column. Then we can convert it into a specific genre, a specific column for per unique value. Now let's look at another way to handle text columns, label encoding. Label encoding replaces each unique text value as an integer. For example, it will give like a pop as a genre. It's gonna give a value like one, for example, rock two, and rap three. The encoder looks at the column and assigns a unique ID for each unique value. Let's use the sub playlist subgenre as a column as an example. If we applied one hot encoding for playlist subgenre, it would create 24 new columns from that single column. Instead, label encoding keeps everything neatly into one column. Let's look at the code for it. I will get the code. Let's run it. First, let's understand the code. The code starts by creating an empty translator called this label encoder. Encoder equal to label encoder. Think of it like a subgenre to integer conversion. The line doing the most of the work is this encoder.fit transform, where we are giving it this playlist subgenre as a column. This actually does two operations combined, fit and transform. Think of fit as a learning phase. The encoder scans the entire column, the entire playlist subgenre as a column, finds every single subgenre and builds a dictionary. For example, it will look at the dance pop as one of the column and it's gonna give it a value. For example, here it gave the value three. It will look at hip hop, indie pop, trap, any of these different playlist subgenres, and it's gonna give it a value. At this stage, nothing in the data frame is gonna change. The encoder is simply learning and mapping. Next comes transform. Transform uses the dictionary created during the fit phase, and it replaces every text value with its corresponding integer. For example, here you can see that album rock it's given to 0, big room 1, classic rock 2, and here it's actually updating the data frame. So encoder.fit means learn the dictionary, and encoder.transform it means use the dictionary to convert the data. Since we almost always use both of them together, this like a dependency libraries sklearn, it has given us like a function to do both of them together, fit or fit underscore transform. So after running the code, the output shows two columns side by side. Here you can see it's two columns side by side. On the left side is the original text value. On the right side is the integer assigned by that encoder. For example, tropical has a value of 22. We have successfully converted our text into numbers. At this point, you might wonder like if machine learning is all about numbers, where numbers are multiplied, division, and subtraction, addition is going to happen, then won't model think that subgenre, like for example, 22 is bigger than album rock, which has value 0, or big room, which has value 1. So model may interpret, like for example, here, let me copy this three. So model may think that Latin pop is more important than Latin hip hop, but that's not the case. That's not true. For us, all the genres have the same value. There's no ranking in it. This makes the label encoding a poor choice for most categorical features. Label encoding works best when categories already have a natural order. For example, if we have an order of like a, small and small, medium, and large. In that case, we can give it values that okay, we can tell encoder to give value small to medium 1 and to large 2. And we know that 2 is greater than 1 greater than 0. Or if we have a t-shirt size as one of the column, like a t-shirt size with small, medium, large, extra large, double XL, or education level. In these cases, converting categories into 0, 1, 2, 3 preserves the real world ordering. For the playlist genre column, there is no natural ordering between genres. Rock is not greater than pop, and pop is not greater than hip hop. The numbers are just arbitrary. Because of that, we are not actually going to use label encoding in our data. I just put it as an example. Now, let's look at another encoding technique called target encoding. Target encoding replaces a category with a meaningful statistic calculated from the data. For example, it might give Ed Sheeran a value of 84 or Drake value of 79, Taylor Swift value of maybe 88. Unlike label encoding, these numbers are not random IDs. They actually mean something. We already translated genres, but we still have another important text column, track artist. Track artist. If you think about it, the artist has a huge influence on a song's success. A song from globally famous artist is usually more popular than a song from an unknown artist. The problem is the dataset contains more than 1,000 unique artists. And if we use one hot encoding, we would create more than 1,000 new columns that would consume enormous amount of memory. If we use label encoding, then it's going to give some completely arbitrary values to all the artists. The model has no way to know whether artist 73 is more popular than a artist 15. Instead, we are going to create something much more useful, a reputation score. We will look at every song an artist has in this data set, calculate the average popularity of these songs, and replace the artist's name with that average. The popularity score already exists in our data set. Here there's a track popularity, but that is per song's popularity, not the artist popularity. So what we'll let's get the data. Let's go get the code first. I'm going to copy the code I have. Uh, yes. So let's look at the code. The main method here is this one. Artist means data frame encoded group by track artist, and we are getting the mean value. So let's see what it is doing. Let's break it down. The first part is group by track artist. So we are just grouping by all the songs from that track artist. For example, let's say Ed Sheeran has three songs. Here we have just one, but let's say it has two songs. Then it's going to basically group both of those songs together. So it will group it for all the artists and their songs together. So for example, you can assume here uh, Ed Sheeran, and it's gonna take its song one, song two, song three. It's gonna group by all the songs. Next is the track popularity. It tells Python to look at the track popularity for each of the songs and then create a mean from them. So let's say if it has like 100 and then 50 and then another 50, it will basically create a mean value from all the songs from Ed Sheeran, and then it will assign that value, the result, to the track artist column. Next, we use basically the dictionary data frame encoded.map with artist means. It will basically like before the track artist add Sheeran. After that, it will just put the value of this encoded value. The text is gone. Let's look at the data frame now. We assign data frame encoded. Let's just display the data frame. Yes, artist popularity score. So here you can see that 74.23. That is the score that was given to Ed Sheeran. So it's song, and then we just created a new column. Later, we will just drop the track artist as a column. But notice how different this is from label encoding. With label encoding, Ed Sheeran will just get some random value, maybe like 15. But 15 has nothing to do with that number. Like the track artist and that number does not have any relationship. But here in our target encoding, the number represents the artist's average popularity. That number contains real information the model can learn from. When should you use target encoding? Basically, use it when the column contains hundreds or thousands of unique categories, and those categories have a strong impact on the prediction. For example, artist name in our case, or zip code or city names, product IDs. Target encoding captures the value of category without creating thousands of new columns. Think of me as a teacher and AI as my student. I want to teach the student how to predict whether a song is worth recommending. Right now, my dataset contains all kind of information about the song. For example, the release date and its playlist, tempo, its duration, its genre. and its subgenre encoded. Plus, now the last one is the popularity score. Now, this is very important. Earlier, we used to popularity to score our artists. That is fine. Like here, this is the one. This is our artist's popularity, not the song's popularity. For example, Ed Sheeran average popularity is 84. This is a clue. It tells the model that Ed Sheeran's songs are usually popular, but telling the AI this exact song's popularity is 67, 70, 60, 69. This is not a clue. This is the answer key. And we don't have a literal skip data from Spotify. So we are going to use this popularity score to create our final answer. Look at the first, let me first put the code here. Yes. Look at the first line here. The data frame encoded with track popularity greater than 50 as integer int. This line creates our answer key. We are saying that popularity greater than 50, it means that people listen to this song. If it's less than 50, then people are skipping it. This specific part of data frame encoded with track popularity greater than 50 checks every song and asks, is the popularity score greater than 50? The result looks like, say, 95 true, 72 true. If the popularity score is 38, it means no, it's not greater than 50. Then it will just assign the value int. It's like it's if it's greater than 50, assign it value 1. If it's less than 50, assign the value 0. This entire column becomes our answer key. So why is this is our answer key? And X is everything except the track popularity. So here we are just dropping the track popularity as a column. So X is our test question, like our data set. Uh, so very soon we are going to split our data. We will give the AI like a 80% of the songs to learn from and hold back 20% for testing. So whenever we want to teach AI, we will teach it with 80% of our data and 20% is for testing our data, our model. If we leave the popularity score, like this, our track popularity column, if we leave it into the AI, AI will just look at that column and it will train on that column. It won't learn the music. It won't learn any patterns. It will simply read the answer and say, yep, recommended. I recommend this song. It will just look at the track popularity. In the future, when a brand new song is released, we won't have the track popularity score available. This is exactly where what we are trying to predict, right? The model will look amazing in our notebook, but completely fail in production. It's basically like model is 90 by 99.9, 100% right in our test data, but always wrong in our 100% right when we are testing it. But it's always wrong when the new song comes out. This problem is called data leakage. Data leakage happens when the information from our answer accidentally leaks into the training data. It ruins our model. So what we are trying to do is cut our data set into two piles. Pile 1 is Y, which is our answer key. The pile 2 is X. This contains our clues, the model that should train on, the model data basically. So here's the X encoded drop. Here we are basically like a scissor cut the answer column out of the data set. Everything except popularity column becomes X. Like all the other columns like tempo and the other things that we saw, duration, playlist genre, EDM, they all stays into our main column. At the end, we have X is the questions and Y is an answer. Like here, X is the questions or our test data and Y is our answers, the popularity score. We still have columns like track name, track ID, uh, and this playlist ID. Now comes the important step in machine learning. We need to remove anything that does not help the model to learn patterns. Remember the rule. Neural networks are just massive calculators. They only understand numbers and patterns in numbers. They do not understand this raw text, like I don't care, or pop remix, or this UUID or track ID that is created for Spotify. These columns are not useful features, they're just identifiers. We already handled the important text columns earlier. We converted genres into one hot encoded column, artist into a numeric reputation score. So the meaningful text has already been translated into math. What remains is noise. For example, track names are unique for almost every row. Track ID are just database identifiers. Keeping them would only confuse the model. Now we act like a bouncer at a club. We decided what gets in and what gets kicked out. We have a here I have created a list of columns that we need to drop, and then we here basically this is a list of columns, and we apply. Remember, X is our data set that does not contain the popularity score. So here we just drop all of the columns from here, from the list of columns, and this is now our and clean data set. Everything else, that noise is removed. Uh, this is the data that we will use for training the model. At this stage, model finally sees a clean structured data set where every column contributes to a real pattern instead of random text. So here you can see everything is just column. Here 1, 0, 0, true and false are also 1 or 0 values. They are not. They are also not actually text. So we have one big data set X, but if we train our model on every single song, we have no way to check if it actually learned anything. It would be like giving a student the exam questions before the exam. They might just memorize the answer instead of learning the subject. So we have to split our data into two groups. 80% of the song, this is what AI studies, and 20% of the song, this is the final exam. The AI never sees them while studying. And then we also have our Y column, if you remember previously, which is our answers. We'll divide this into also 80-20, which is Y underscore train. We'll give it that it's 80% of the answers from the questions from the data that we trained on, and 20% is the final exams answers. We hide this to see if AI can correctly guess them. So let's get the code for it first. Um, Okay, so here it did slicing the data into 80% training, 20% testing. So let's look into it. Here X math only. X math is our data set, the final data set, and Y was our answer key. Let me name it something else. X math X final data only. I have to run this and then run this. Right. So we are handing our machine the clean list of questions X final data and our master list of answers Y. And test size equal to zero point 0.2. This is the slicing instruction. We are telling the machine put exactly 20% of the data into testing pile and remaining 80% into training and random state as 42. Here, this is just a shuffle lock. So before splitting, the machine shuffles all songs like card of deck of cards. So it's not like first, it's just going to take first 80% and then rest of the 20% is going to give it for testing. It will shuffle the data. And if you enter the code like 42, the lock opens like this. Think of it like a random state 42 as a combination lock. And if you enter the code 42, the lock will open every time the same way. So enter 42 again, the shuffle will happen and we will get the same result. So in plain English, we are telling Python, shuffle this data, but use the 42 pattern. So my results stay identical every time I run this code. And when we run this cell, it prints out exactly how the songs were divided. Training pile X train, 80% of the songs, total songs, and the remaining are the 20%, 6, 5, 6, 7 songs. Now let's look at the next phase, which is like a feature scaling or the equalizer. So remember during the training when we told that the machine learning model is really just addition, multiplication, and subtraction. It's a huge calculator. So imagine one column here, our song in our song. The tempo column has values 122 or 99, 124. But if you look at the liveness, its values are zero point 0.06, 0.35, 0.11. So if we feed these numbers directly into the AI, the math will assume 150 or like 122 is more than zero point 0.06. So it's more important because it's a bigger number. It will simply ignore the liveness or instrumentalness, acousticness, speech and all the other values because they all are smaller than tempo and they are much more smaller than tempo. So we need to force every number into the same playing field, usually between 0 and 1. So the AI treats every feature as equally important. To do this, we use a tool called min-max scaler. It looks at the column, it takes the lowest number and it turns it into 0, and takes the highest number and turns it into 1, and squishes everything else proportionally in between. So let's look at the code for that. So this code does the main max color here. We're just initializing it. The main thing here is fit transform. Fit transform on our X train data. X train. This is our training data, the 80% of the training data. So the computer looks at the X train, the training data, and learns the boundaries. For example, it learns the minimum tempo is 60 and the maximum tempo, for example, is 180. Then it applies the scaling formula to X train data set using those numbers. Uh, and then the next step is the transform on the test data. But in the test data, if you see here, there's no fit. Why there's no fit? Because if we run fit again on the test data, then the computer would calculate the brand new minimum and maximum just for the test data. Let's make this concrete with the example. During testing, if our minimum energy song is 60 and maximum energy song is 150, so in our test data while we are testing, we will use that as min and max. If we take into account the testing data also while calculating, and during testing, let's say if our one of the high energy song is 200. So during testing, if we do the fit transform, our now new maximum is 200 instead of 150. So now the whole AI model, while it's training, it used the value of 150, max energy is 150. But while testing, we just change the meaning of that column. So that will cause the issue. But think in case during training, the max energy was 160. But during testing, the new song came out and the new song's energy is 200. Then we just plug it into the same formula, the same transform formula, and it will put some number like maybe more than one, maybe 150. It's a super energetic song. The AI understands that perfectly. So we do not recalculate anything. We just plug 200 into the same exact formula, and that was built using 160 as a or 150 as the max energy. So to summarize, fit learns the numbers. When we run fit transform on training data, the computer calculates and memorizes the minimum and maximum boundaries of the training set. Transform uses those numbers. When we run transform on training data, the computer is strictly forbidden from looking at the new data's boundaries. It blindly applies the exact same training boundaries to the new data. This keeps everything mathematically consistent, fair, and ready for the neural network to learn. Now here you can see that our output was done. The scaling is complete. So here let's look at the data set that is the final result that is created. So final result is now it's actually moved away from our data frame pandas and now it has created a NumPy array of X train scaled. Here you can see that all our columns and everything is gone. This is our first row basically, and first row everything is, if you can see here, e raised to 0.01 minus or e raised to minus e raised to 0.5 or 1 plus 0 minus 1. So everything is now in the range from 0 to 1. If we want to look at the data in the data frame format for us to better understand it, let me put the code here. And here you can see that everything, the whole first row and all the first five rows, they all are either between 0 and 1. Nothing is more than 1. Here you can see that our true and false previously, they're also converted into 0 and 1 values. So now all of our data is in the same playing field, you can assume. Next step is where we will look into the training part of the data set. Till now, we have been preparing data. We cleaned it, we encoded text columns, we prevented data leakage, we scaled our feature. Now it's time to build the actual neural network. But before we deep dive into that, first, what is neuron? It's the word neuron comes from biology. The brain controls billions of neurons. So biological neuron receives signals from other neurons, processes those signals, and then send the new signals forward. For example, imagine you accidentally touched a hot stove. For example, this is hot stove. If you accidentally touch it, it's gonna send this data to one neuron one in your body. It's gonna send it to neuron two, and that same way it's gonna send it to different neurons, and in the end it will reach our brain. Now the neurons pass these electrical signals from one neuron to another until the information reaches our brain. Then our brain quickly decides, okay, this is hot, and sends another signal back through neuron to your muscle and move your hands away. All of this happens in a fraction of seconds. A neuron in neural network is inspired by this idea. It's not a real brain cell, but a simplified mathematical version of one. Think of it as a tiny mathematical calculator. Its job is simple: receive information, process information, produce an output. For example, suppose we want to predict whether a user will listen to a song or skip it. A neuron might receive information such as a song's tempo, artist popularity, time of the day is evening or morning or afternoon. One neuron, it takes all of this information from that one song, performs some calculation, and produces an output. And just like our one single brain neuron cannot do everything by itself, a single neuron, artificial neuron, is also very limited. It just looks at one tiny bit of data. The real powers come from connecting many of these neurons together. A neural network may contain hundreds, thousands, or even millions of neurons working together to solve a complex problem. Every neural network is ultimately built from this mathematical calculators, like a tiny neurons. The next question is, what is the input to this neuron? The information entering a neuron is called the input. Think of input as the facts or clues that neuron uses to make a decision. Specifically, in our case, this all of this, like a danceability, energy, key, loudness, mode, speechness, acousticness, all of this, the full row is input to the neuron. Uh, and in machine learning, we write it as like a x, like xi. We write it as x of I, like x of 1 as the first input, x2 as the second, basically column, first 0.37, 0.37, 0.65. Because the neuron itself does not know what is energy or what is key or what is loudness. They just simply knows numbers. It doesn't know anything else. Its job is to figure out how important each of this number is. So neuron needs to figure out that okay, energy is important, so that this is what I should, when I make a decision that will customers going to skip the song or not, it will determine which specific parameter has high weightage, which specific parameter has low weightage. The next question is, what is weight? Not every input is equally important in our song. For example, here, danceability, energy, key, loudness, mode, all of that are not equally important. We can't say that all of them have a specific point that, okay, danceability is 0.05, energy is 0.05, key is 0.05. They all are equally important. They all are not, because they all have, for a user, some user, liveliness is more important. For some, instrumentalness is more important. Imagine you are deciding to whether to watch a movie, you might consider movie rating, favorite actor, release year. Some of this factor might matter to you more than others. The same idea exists inside a neuron. Weight tells the neuron how important the input is. Think of a weight as an important score. For example, let's say weight is W1 is 0.01, W2 is 0.05, and W3 is -2. These weights correspond to our input. For example, here W1.01, then it's saying that for our danceability, the weight is 0.01 for neuron 1. For energy, for song 1, the weight is 0.05. For key, the weight is -2. Notice that the weights are different. This means that neuron does not treat every input equally. Some input influence the decision more than others. A larger weight means a neuron pays more attention to that input. A smaller weight means neuron pays less attention to it. Weights can also be negative. A positive weight pushes the prediction upwards. A negative weight pushes the prediction downwards. For example, popularity weight. For example, let's say there's a popularity weight of plus 0.05. This means that higher popularity increases the chance of listening. But let's say there's a time, duration of song, and its weight is -2. This means that at this time of the day, the user is more likely to skip the song because it's a negative effect. And remember, -2 is not a time uh, for machines. We basically convert this into like the machine does not understand this is afternoon or evening, so we convert everything into the time, also into the some kind of a number that a machine can understand. But the important thing to understand is this: the weights are what the neural network learns during the training. At the beginning, the weights start as a random number. The neural network has no idea which inputs are more important and which ones are not. It makes a prediction using those random weights and then compare its prediction against the correct answer. For example, suppose a model predicts that listening probability equal to 90%, but the correct answer is skip. Let's say the correct answer is user will skip this song. So we predicted that Our prediction, our model prediction was that 90% user is going to listen to this song. But the correct answer when the model was training, it saw that user just skipped this song. The model was clearly wrong here. So machine learning looks at the output and measures how far away the prediction was from the correct answer and then adjusts the weights. If a particular weight contributed to the mistake, the model may decrease it. If a particular weight helped to make the correct position prediction, the model may increase it. The process happens over and over again for thousands or even millions of training examples. For example, a model may eventually gradually discover that an artist's popularity is more important and increase its weight. Or it may discover that time of the day is not useful and decrease its weight. Over time, the weights slowly improve. The neural network become better and better at making the predictions. So when people say the neural network learned something, what actually happened is the neural network learned better weights. The knowledge of the way model is stored inside those weights. This is why after training finishes, one of the most valuable things we save is learned weights because they contain everything the model discovered from the data.
Now let's look into bias. There's an important part inside every neuron, that is bias. Think of bias as a flexibility knob for the neuron. Even if every input is zero or like too weak or towards zero, bias push the decision either way. The neuron needs a way to shift its output. Bias gives it that. It moves the neuron's output up or down, completely independent of whatever the inputs are or weights. Now the question is, why can't the weight just handle this, right? We already talked that weight can push the output either up or down. So why do we need bias? Let's take a simple example. Imagine a neuron that only looks at one feature or input, energy. For example, energy is our input, and energy value is always between 0 and 1. Since energy cannot be in minus 1, so energy is always 0 or 1. And let's assume the weight of this input is 2.8, for example. Now without bias, how will our output look like? Output will be 2.8, the weight cross whatever is the input or energy value. Now look at what happens at energy 0. Let's say energy is 0 for the song. Then our output is also 0. The same way, let's say input is 0.5. Then our output is around 1.4. And let's say our energy is 1. The song's energy is 1. Then our output is 2.8. Right? Later we pass this output of the neuron into an activation function. For now, think of activation function as like if the value is negative, uh, activation function. If value is negative, then it means we will skip, probably we will listen the song. And if value is positive, then we are more likely to skip the song. So the exact point where output crosses from negative to positive becomes the model's decision. So for example, you can see here that our output is always positive across entire range of energy values. The moment energy ticks up even slightly above 0, so you can see that for us, the output will never go into minus 1, minus, even like, so it will always start from 0 because energy's value is always start going to be between 0 and 1, and so output will always be 0 or more than 0. The model never gets a chance to predict that a user is going to listen to the song, because for us, if output value is negative, it means that user will listen to the song. If output value is positive, it means it's going to skip the song. But in our case, it's never going to go into minus 1. Now let's see. Now the other question is, can't weight change this value? Like, can't weight uh, turn this into negative? Because we already talked, right, that weight is going to be trained across our training data, and it will change the value over time as we run our model. Weight is going to adjust the value. So let's say weight is negative, right? Out of 2.8, if weight value is minus 2.8, for example, let's say energy 0 for that song, it's still going to be 0. If 0.4 and the weight is minus 2.8, in that case our output will always be in the minus, because minus 2.8 cross whatever is the input or energy, which is 0 and 1, between 0 and 1 will always be in the minus 1. So basically here we have hit a wall. Weight alone, no matter how it's trained, cannot move this neuron decision boundary off of 0. So the neuron is forced to behave this fixed way. It has no freedom to adjust where its decision starts. In real data, patterns are rarely that perfect. Maybe the real rule is people only start skipping the song after energy crosses 0.5. So they don't skip the song if energy is between 0 and 0.4. They will listen to that song. For in our case, they will skip the song if energy starts from 0 itself, right? So let's say we add a bias now. So what's going to be output equal to, for example, the bias value that is calculated while training the data for our neuron is 1.4, for example, and the output value is 2.8, our weight cross energy minus 1.4 value. Now let's say how the behavior changes. At energy 0, the song output is actually minus 1.4, not 0. At 0.5, output is 0, and at 1, output is 1.4. Now something important happens. You see the crossing point just moved from energy 0 to energy 0.5. So previously, energy 0 was the one that decides either it's going to be turned positive or negative, because after energy 0, it's going to always turn to positive value. The output is always going to be positive. But in the case when we add bias, if energy is 0.5 for that song, then it's going to turn to 0, and after more than 0.5, it will always be positive, and before 0.5, it will always be negative. So bias basically lets the neuron decide where should I start being active. Without bias, the fixed starting point, and with bias, the flexible, we can put the starting point anywhere. So here we put the starting point at 0.5. Without bias, it will always be at 0. So the same way we saw weight value gets changed while model training, the bias value also gets updated while model training each neuron. Now let's say we combine everything that we have looked together. The neuron takes input, multiplies them by weight and add bias, and that process produces a single value. So if you want to look at that, for example, what is the final value of the neuron? What is the final formula for neuron? It's Z, which is output, equal to weight 1 and x1, which is input, plus weight 2 x2, weight 3 x3, plus bias, the last one, where x is the input and weight is the weight, basically w is the weight, b is bias, and z is raw output. For example, let's say we take an example. We have total 3 inputs, which is tempo, song tempo, which is 120, song popularity, that's 80, and songs time of the day, when user listen to the song, is 0.7, for example, and the weight for each one is, let's say weight for tempo is 0.01, weight for song popularity is 0.05, and weight for time of the day is equal to -2, for example. Then what's going to happen in the end? And bias is 1. Okay, bias important. What will happen is in the end 120 cross 0.01, because the for tempo the weight is 0.01 plus 90 song popularity, and its weight is 0.05, and day is 0.7 and its weight is -2 plus 1. This is the formula for neuron 1's output. Now let's look into it that why one neuron itself is not enough. A single neuron is extremely limited. It cannot learn it can basically only learn a simple rule like if popularity is high then recommend the song. But real human behavior is much more complex. People love EDM but only at night, or they skip the sad song when they are happy, or they like an artist but dislike the certain genres, or like people can change the taste based on time and mood. So one neuron cannot capture all of this. The same way, like in our body, one neuron is not doing all the job. Most of multiple neurons are connected with each other. So instead, we use many neurons that work together. For example, the input one will get passed down to neuron one that detects, for example, tempo pattern in song. The same thing gets passed down to, let's say, neuron 2, same input, 3, 4, 5, that detects mood, tempo, that detects genre pattern, that detects, look at subgenres preferences. Something is like time of the day. So there will be multiple neurons here for one input. Think of it like basically it's a this is the thing that makes the neural network powerful, because we do look at all the things that are there into the that can basically affect the output, that can basically say that hey, is user going to skip this song or user is going to listen to this song. Now what is actually a layer? Let's look into that, because layer is important when we are building a neural network, and this all we will connect it in the end to what is exactly neural network and in our code. Now that we understand what is neuron weights bias, we can look into what is layer. A layer is simply a group of neurons working together. Think of like a team. Each neuron looks at the same input but learns a different pattern. For example, here neuron 1 is going to learn the mood related pattern, neuron 2 is going to learn the tempo related pattern. Basically a layer processes this and produces a few transformed version of the data. So like input that goes into layer 1, then it basically creates a new it's going to create an output that will be a new input to the next layer. So instead of raw data, the layer creates more meaningful version of that data that gets, and let's say if we have 4 or 5 layers for a neural network, each layer once output is going to be input to the next layer. So a layer does not make the final decision, it only transforms the data into something more useful for the next step. Now let's say if we have this line, for example dense 32, what it means, it creates a layer with 32 neurons. So 32 neurons working together, each neuron learns a different pattern from the same input. So full idea of the dense layer is means if every neuron is connected to every input feature. Suppose our dataset has 10 input features. For example, let's say I have it here I1 to I10. These are our input features. You can assume it's like either like a song or genre or tempo and liveliness of the song. And the same way we have total, for example, 10 different features. And suppose we want to create a dense layer with 8 neurons. So what we write in the code is basically dense 8. Visually it looks like input to layer. So like input I1 to is neuron 1 I10. Every neuron receives 10 inputs basically. So when training begins, the neural network knows absolutely nothing about the data. So every neuron starts with random weight. So for example, neuron 1's weight is, let's say this is neuron 1's weight, and neuron 2's weight is equal to something like this, for example, and neuron 3 weight, it's a random weight when it starts with, it's absolutely random. Now each neuron has its set of weights. That is why different neuron learns different paths. For example, neuron 1 compute will be Z1. For neuron 1 compute is W1 cross I1, weight 1 which is 0.5 and the I1 which is input, and weight 2, weight 2 and I2, weight 3, I3. That same way, it's basically weight 1. So weight 1, 1, weight 1, comma 1. It means that weight neuron 1's weight 1, neuron 1's weight 2, neuron 1's weight 3, neuron 1's weight 10, this last one, plus bias in the end. The same way we'll have for neuron 2 is neuron 2, its weight 1 which is minus 0.4, neuron 2 weight 2 which is 0.9, and initially all the neurons will connect to the same input. The input will stay the same. So this is for one song. For one song we have this as an input. And now assume we'll have like thousands of songs, and each song will have 8 neurons, and each neuron will have a random weight. So after all the 8, so let's say for that one song, after all 8 neurons finishes calculation, the layer 1 will produce output something like this: Z1, Z2, Z3 until Z8, which is the output from the neuron 1 or our layer 1, which is dense 8, and this is for song 1, right? This output become input to the next layer. So suppose our next layer contains 4 neurons. So the second layer receives Z1, Z2, Z8 as an input, and again every neuron in the second layer starts with its own random weight. So let's say now we have a dense layer at 4, and layer neuron 1 for layer 2 will start with just 4 weights only, 8 weights, because our input is only 8 now. So instead of 10, it will start with weight 8, and here it will be random, anything, 4 and 1, 2, 2, 3, 4, 4, something 5, 1, something like that. And the same way now we'll have neuron 2, 3 and 4, 4 neurons, and all these 4 neurons will have an output of Z1, C4. So now we have the four of this layers, and in the end we'll come back to only one layer 1, which is the output. Output will be our Z1, layer 1. This will go into output, will go into activation function. We'll look into activation function later. But the main question is, how does the network learn in the whole process? So initially all weights are random. The network makes a prediction. If it then compares that prediction with the correct answer. So for example, our prediction in the end, like the Z1 output came up as 0.90 for example, and the actual answer is 0 for that song. It means that it's not popular at all. So the model was wrong. So it calculates how large the error is and works backward through the network. So the network asks, like the whole neural network asks, which weight contributed to this mistake. So let's say it comes out that this is the weight that contributed most to the mistake, and which weight should be increase or decrease. So it's going to say that, okay, 0.8 here weight for the third input in layer 1, we should increase it to maybe 1.5. That way we will be more near to our actual answer of 0. And we have a libraries for that. Like in Python we have a TensorFlow. This calculates this adjustment automatically using a process called backpropagation. Over thousands of training examples, the random weights gradually become more useful, and the learning process is what allows the neural network to discover patterns in this data. This learning process, the weight, and remember the weight will be same for all the songs. So for here when we say neuron 1's weight, it's not going to be a different weight for each song. All the thousands of songs, they all will going to be used the same weight for layer 1. For layer 2 again, they all will be using the same weight, but every neuron will have a different weight, but all the inputs or all the songs will use the same weight. Now there's an interesting thing called parameters. So let's say we have 10 inputs, we have 10 input, and we have 8 neurons. So how many weights is total? It's 80 weights that we have total, because each input will have 8 neurons. So 8 so like 10 random weights per neuron, which is 80, right? For layer 1, it means total plus we will have 8 actually bias values because we have 8 neurons. It means that for layer 1 we have total 88 parameters. The word parameter in neural network usually means weight plus bias. So when people say that 2 billion parameters, what they mean is the model has roughly 2 billion learned numbers, mostly weights plus biases and few other learned values depending on their architecture. But then why so many? Like 2 billion, that's huge. Think about our music, like our Spotify model. We have like how many? Maybe 20 features, which is like tempo, energy, danceability, artist popularity, or genre and others. But a large language model like GPT and Claude is much more complicated. What they have to learn is grammar, spelling, facts, reasoning patterns, language transition, writing style, relationships between words, and so many more. So that requires a huge number of learned connections. A parameter is simply like a number or the neural network is allowed to adjust during the training. Learning is a process of finding the best value for those numbers. So our tiny neural network will have like 100 parameters, but a medium neural network will have 100k parameters. Large neural network might have like 100 million parameters, and modern like this all LLMs, they will have like billions of parameters. The neural network's final output for each song is just a mathematical score. So for example, the final output for song 1 can come out as 5.8 or 10.8, something like that, once it goes through all the neurons and all the layers. But we need to convert it into something meaningful because that is just a number at this point. This is the job of activation function. Think of it as a decision filter. It decides should this neuron fire strongly or weakly. One common activation function is sigmoid. It takes any number and convert it into a value between 0 and 1. So let's say here the same example. Let's say z is equal to 5.8, 5.8, right? And once it goes through activation function, it will become number between 0 and 1. So let's say it becomes 0.992. This means the probability is at 99.2%. So here it's saying that the neuron is saying that I'm very confident, I'm 99.2% confident that song user will listen to the song. So the question is why activation functions are even needed. Without activation functions, the neural network would just be a bunch of linear equations stacked together. A linear model is basically this, like output equal to a cross input plus b, right? So in our case, output was what? Input cross weight plus b. Just if you think about it, this whole equation will always produce a straight line in graph. So if input increases, the output is definitely going to increase. So for example, here let's say input is equal to 1 and weight equal to 2, bias equal to 1. So our function output will be what? 1 star 2 plus 1, which is 3. Now let's say our input increases to 2, it's going to be 5. The same way if output increases to input increases to 3, then it's going to be 7, 6. Yes. Here it's going to be 5, right? So here if you think about it, the whole output for us is it's a straight line. But in real life, it's not a straight line. Like all of this outputs, they are never a straight line. Sometimes example is like a song is skippable behavior. It might look like this. If the, let's say for songs energy is low, then sometimes user will skip. But let's say its energy is medium, then it's mostly a user is going to listen. And if energy is high, then also it can sometimes user will skip again. So it's not a straight line. Basically it changes. There are curves. So sigmoid slope or curve means how much the output change for a 1 unit change in our z. So let's say if z increase from 3 to 5, 5 to 7, or 7 to 9, or 7 to 8, how much the output changes for the 1 unit in z is not fixed. It changes depending on where z currently is. That is the entire definition of curve, a changing rate of a change. Let's take it as a good example, right? Um, let's say if z value is around this. So for, let's say our z equal to 0, like our output equal to 0, output equal to -1, and then output equal to 1. And in that case, what sigmoid function is going to give us, for example here is 0.27, here this is going to give us 0.50, this will give us 0.73. So moving z by 1.1 literal, like from 0 to 1, we are changing the output. If you see here 73, 50, we are changing the output by 0.23. Now let's say if we increase it more, right? Z equal to, output equal to 2, 3, 4. In that case here the output is going to change by 88, 95, and then 98. So here if you see here, moving Z from 3 to 4 only change the output by about by 0.03. So same size step in Z, like 1 unit both time, from 0 to 1 it changed by 0.23, but from 3 to 4 this change by plus 0.03. Here the it changed by 0.23, right? It's widely different size step in input, in output. So near the center, like near the center is where the sigmoid functions are very sensitive and react strongly near the edges. It's almost flat, barely reacts at all if it goes to like the edges actually. So here for example, let's say this is -1, and this is 1, right? So if you see here, in this case it doesn't change a lot, but near our edge here it's changing a lot. The sigmoid function is reacting a lot in this case. So activation functions break the straight line behavior they introduce. So if we don't have the activation function, how our graph will look like is kind of like this. If we have this as a graph, our data will just look like this. It will be a straight line. It won't be like a data between this way, where near the edges our output is going to be like very slowly it's going to change. So this activation function introduces curves and bends into the model. So instead of straight line, you get curve function. There are other types of activation functions other than sigmoid, which are ReLU, softmax, or GELU. Now let's look into the code. Before we deep dive into the code, we will be using mainly two libraries for this very simple initial code. One is TensorFlow and other one is Keras. What TensorFlow handles? TensorFlow handles matrix multiplication and gradient calculation. So basically gradient calculation is a direction sign of for learning. So it tells the network whether a weight should increase, decrease, or stays the same. Uh, for example, like imagine a student takes a test and scores 40%, right? The teacher doesn't just say it's wrong. The teacher says you need to study algebra more, or you need to study geometry less. Basically the thing that we discussed, right? We have to change the weight and we have to change the bias. It's the feedback that tells student what to change. A gradient is exactly that kind of feedback for neural network. Suppose a neuron has weight of 2. After making a prediction, the network discovers prediction was too high, then the weight is going to change from 2 to 1.8. So here in our case, TensorFlow is the one that's going to do it. A neural network can contain, like billions and millions and thousands of weights. So after every training example, TensorFlow calculates which weight helped, which weight hurt, how much should each weight change. These are all gradient calculations, and TensorFlow is the one that will do it for us. TensorFlow also handles GPU acceleration. So training a neural network requires enormous number of calculations. As you know here, it will require a lot of multiplications, sum on this inputs and weights and random numbers. So think about a model with 100k weights. Every training step requires thousands or millions of multiplications and additions. A normal CPU cannot do this, it can be slow. So that's why GPU was originally designed for video games where it needs to perform many calculations simultaneously. Neural network have the exact same need, and TensorFlow can use GPU to perform many calculations in parallel as well. And that's why if you see here, let me reconnect to our Google cell. It will also show us the option of GPU and CPU both. So CPU is like one worker solving solving problem one at a time. There can be multiple threads and multiple cores into CPU, multiple threads or cores. But GPU is like a thousands of workers solving problems at the same time. So, and other than GPU acceleration, TensorFlow also provides model saving and model deployment. Model saving, it means that training a neural network can take minutes, hours, or even days. So after training finishes, we don't want to lose all the learned weights and learned biases. So TensorFlow allows us to save the trained model to a file. And model deployment. So deployment means taking a trained model and putting it into a real application. Without TensorFlow, we would have to write, like thousands of lines of mathematical code ourselves. And Keras is like a high-level API built on top of TensorFlow. So think of Keras as a steering wheel. TensorFlow provides the engine, like car engine. Keras gives us a simple way to control it. Instead of manually writing, complex neural network mathematics, Keras allows us to build networks by stacking layers together. So let's look into the code now. Next, uh, let me just create first import the TensorFlow as TF from TensorFlow dot Keras import sequential put dense and drop out. So let's create the model here. Model equal to sequential, and now we'll just create an layer on top of it. This is the first input layer, which is says dense unit equal to here. This is like a unit, which we are saying that we need 32 units like the input layer. Activation function we are going to use here is ReLU. Input shape is x train scaled and shape 1, which is our x train scaled is the first that we had put x train scaled. Yes. Next we will add like a second layer here, and I will add the third layer here as well. The second layer, let's say we want it as a 16 layer. We don't need extensions. We need we need one. Let's say the last one is only one as an input layer. Let's look into the code. First, we created the model as sequential model. This is just telling Python that build a neural network step by step, layer by layer, sequence by sequence, where data flows from input to layer 1 to layer 2, and finally we need output. Next step is the dense model.add unit 32 activation value and input shape, right? This is just our first layer where we are saying that for layer 1 we need 32 neurons. Now this is the decision that you have to make. You as a person who is developing the model, you have to make that how many layers deep that you want to create your model. You want like a 256 layers, you want only 16 layer, you want maybe 8 layer or maybe more than 256 layers. Next is activation function. What kind of activation function that you need to use here? Here for us, I mean for simplicity, I just use the ReLU because it's extremely simple. It says that if output is less than 0, like if Z value is less than 0, then just put the output is equal to 0. So input for the next layer will be 0 for that neuron. And if output is greater than 0, let's say output was 500, then that will be the output for the next layer. That will be the input for next layer, because it helps the network learn complex patterns efficiently. It's also very fast to compute. That's why ReLU is most common activation function used in hidden layers. Now this one input shape, right? X train scaled. Let's print it out. Printing is 19, which is our actually the input. So if we just print the shape itself, it's going to give us that what is the number of rows and the number of input like columns for our X-train scaled data frame, right? So shape 1 is just going to give us the 19. It's just telling it that there are 19 inputs that are there per song. So you see next where we are not putting the extra, like the input shape, because Keras already knows that for the model 1 layer 2 the input will be the output of the layer 1, which is 32. For layer 3 we are just putting that we need as a layer 1. We are also not putting anything here, but here we have to change the function, the activation function, to sigmoid. Why sigmoid, right? Because um, we want specifically, like, we want a probability. Sigmoid converts any number into 0 to 1, as we looked into previously, right? Here it's going to convert it between range of 0 to range of 1. ReLU basically converts it into whatever the number is. Let's say output was 500, right? So output of ReLU will be 500, but in the layer 3 we just have one neuron. We need this as the output. So it's going to say that it will just put the output between 0 and 1. So for example, let's say neuron 1's output was -8, then it's going to convert it into 0. Maybe 003. Output was 4, then it's going to convert it into 0.92, I don't know, any number, right? So now we can interpret this as 92.20, 92.42%, something like that. So that is the probability. So now because we need the probability in the end, like between 0 and 1, and let's also print here model.summary, right? Let's try to run it, and it did give us some error. Let me see what is the error here. uh, Explain scale df dot shape of 1. Dense initialization is missing. Here this is units, not unit. Try to run it. No, cannot convert 90. Oh, it's not input shape, it's input dimension. Same as units, not unit. Awesome. So here you can see the output here. First layer we have the 640 parameters, because 32 cross 19, 608, plus we had 32 as our total biases. So our total parameters were 640 for layer 1, 528 for layer 2, and 17 for layer 3. 17 because we had 16 inputs, we had one neuron plus one bias for that one neuron. So it's basically 17 total parameters. Total parameters for the whole model was 1185, and trainable parameters is also 1185. So model.summary prints the blueprint of our neural network. It shows that what layers are there, what is the parameters per layer. For layer 1 we have 640 as parameters, which is 32. We have a first layer is 32 cross, we have 20, we have 19 edges, so 19 cross 32, 628 plus 32 bias, which comes down to 640 as our total parameters for layer 1. Layer 2 we have 528, layer 3 we have 17, because we got 16 as an input from the first layer plus one bias. So uh, now we have built the structure of our neural network. Think of it like we are building a brand new car factory, and we assemble like the engine, the wheels, the steering wheel, the seats and everything. But the car is fully built, but we still hasn't driven the car anywhere. Similarly, our neural network now has like 3 layers, total 49 neurons plus 184 train parameters. However, every weight still has random number. The model has not looked at saying single song yet, so it doesn't learn anything yet. So after building the brain of neural network, we now need to tell it to learn, right? And this is where we'll have to compile the neural network. Now we need to teach the network how to learn from it. Learn. So let me write another cell here, and model dot compile. Optimizer is hidden, loss is this one, metrics for accuracy, correct. Let me first run all. Let's wait 1 minute, maybe it's connecting. Google Colab is connecting. Should be done in like a 1 minute or stuff. But let's dive into the code. Um, let's first look at all the parameters here. First one is the optimizer, which is Adam. First of all, what is optimizer? Optimizer is an algorithm that updates the weights and biases after every prediction, so the neural network gradually becomes more and more accurate. The neural network makes the prediction. It then compares the prediction with the correct answer. The optimizer decides which weight should increase, which weight should decrease, and by how much. It also looks at the biases and decides the value for bias. You can think of an optimizer as a coach that slowly improves the neural network after every mistake. In our project, we are using Adam, optimizer equal to Adam. Adam is one of the most popular optimizer in deep learning. It automatically chooses good weight and updates and usually trains neural network quickly and reliably. There are other optimizers available as well, but we can maybe learn it later, or we can hopefully look into it later. The second instruction we give during the compile is loss function. For us, it's binary cross entropy. Before the neural network can improve, it first needs to know how wrong it was. That is exactly what the loss function will do. A loss function is simply like a mathematical way of measuring the difference between the model's prediction and the correct answer. Think of it like a teacher grading an exam. If a student gets every question correct, they receive a perfect score. If they get many questions wrong, they lose the marks, right? The loss function does the same thing for neural network. It gives the model a score that tells it how good or bad the prediction was. For example, suppose our model predicts like prediction equal to 0.95. Let me write it here. 0.95, and the correct answer is 0, right? Which is basically skip the song. In our case, skip the song. The model was very confident here. When it says that 0.95, it's like 95% probability user will listen to the song. In our project, we are predicting one of the two possible outcomes, right? Listen or skip. Since this is binary possibility, we use binary cross entropy. It is specifically designed for problems where there are only two possible classes. The goal of the training is simple, like make the loss smaller and the smaller after every training iteration. During the compile and during the training, it's basically trying to make that loss smaller. And the third instruction is during our compile function is matrix accuracy. So the loss function basically helps the neural network learn. We also want an easy way to see how well the model is performing. This is the job of the metric. In this project, we use accuracy. Accuracy is it basically answers just one question, a simple question. Out of all the predictions the model made, how many were correct? For example, suppose the model predicts 100 songs. If it predicts 92 songs correctly out of 100 as an input, then its accuracy is 92%. But let's say if it predicted 65 songs, then its accuracy is 65%. The difference between loss and accuracy metric is loss is used by the neural network to learn. Loss is used by neural network to learn, while accuracy is used by us to monitor how well the model is doing. So it's not used uh, by the neural network, right? So during training, Keras will show both the values after every epoch. Like ideally, it will show that loss should gradually decrease and accuracy should gradually increase. But model.compile, okay, we have actually moved way ahead. But first, let's see, model.compile doesn't perform any learning. Think of it like it's just filling out a setting before starting the game. It simply prepares the neural network for training. Like it tells us that which optimizer is going to be we will use during the train, which loss function, which metric that we will use. Now the next step is where we will actually train the model, which is model.fit. Let me write the code for it. Model.fit, and our parameters are xtrain. That was our. I'll just put our training data set that we had. Xtrain scale is our training data set. Our y train is our answer for the train data set. epochs equal to 20. I'll come back to that one later. Let's do 20 runs. We don't need this. And batch size is 32. Correct. Okay. So what is this model.fit? Actually, we'll look into all of that. Uh, but when model.fit starts, the neural network looks at the training data, it makes the prediction, it calculates the loss, and uses an optimizer to update the weights and bias, and repeats this process over and over again. So think of fit model.fit function as a meaning like fit the neural network to the training data. So when we tell model.fit, TensorFlow starts like complete like a learning cycle of it. It training data, it looks at that and then it finds the random weight. It makes the prediction of that okay, what should be the value for that song, right? Is it user going to skip the song or is it going to listen to that song? And then it compares it with the actual answer. It calculates the loss and it updates the weight and it repeats it again. Like it repeats that okay, did it learn or not? And so here what epochs 20, right? It means that the model will study the entire dataset 20 different times. So for example, oh, did it again. We'll write it here. Let's say epoch 1, right? Epoch 1, it will look at song 1, song 2, up to song 20,000, or whatever our number was, right? Now it's going to start epoch 2, which will again look at all these songs up to 20,000. Then epoch 20, which will again look at all these 20,000 songs. So here there will be like all the other from 3 to 20. Right. Our next parameter into the model.fit is batch size, which is 32. So what it's saying is model is not going to look at all these songs and then it's going to make the prediction and calculate the mistake. What it will do is it will look at first 32 songs, batch of 32, then take the first 32 songs, then make the prediction, then calculate the mistake, update the weight, take the next 32 songs and repeat. So the learning happens every 32 songs instead of waiting until the very end. So if you have let's say 20,000 songs, then approximately we will have like a 625 batches. In our case, we have 821 batches, right? So 821 cross 20, that's like 16,420 is our uh, number of songs that we have divided in our training data. Uh, yeah, let's look at our answer. Our answer accuracy is 0.57 and the loss is NN, which is actually the same across everything. So almost the model is not learning at all. And we can see here it's interesting that loss is not like NN, like null, and the accuracy is not improving. So this is a sign that something is wrong in our data going into the neural network. When the neural network sees like this invalid values like missing numbers or undefined values, it cannot calculate proper gradients. That completely breaks the whole learning process. So because the model is not improving, it's just stuck somewhere. And let's look into the what exactly is the issue, right? Definitely some issue with our data that we have put the data. We first need to check like the data set, is there any missing value or not? So let me put into our X math, which was our data set X. Um, no, it was something X final. Yeah, X final data only. Uh, so before we train the data, let me put it here, right? Let me just print and see the only dot is null. Is there anything null in it? And how many sum? We'll just sum it out to see how many null values are there. Oh, perfect. Artist popularity score, right? So you see here that artist popularity score, this column had missing values. It had null values. And the problem is a neural network cannot work with the null values. So we have to either like we have two options. We have to see how this were like probably almost 5 rows that were null. So either we can get rid of those 5 rows, or we can just put some unknown value there. So let's see. Artist score had 5 rows which were null. So artist popularity score, we were calculating it from the track artist column. So it's possible that some of the track artist column is just unknown. It has unknown values. So let's do this. Let's fix it. We'll just replace the artist encoded with track artist column. We'll just put unknown value here. So it's not null now. And replace df encoded of track artist with that its own. So now every song that has artist value, even if it's unknown, it so basically if there's a null value, we'll just put it as unknown. Let me do run all, and it did run. Here now you see the print x data only, the artist popularity score come down to 0. It means that okay, there is no null value here. Now let's see how our data. Okay, now you can see that our accuracy and loss score is not anymore. It's not null, and our accuracy is slowly improving with every epoch that's going on. Um, so here you can see that at the first epoch our accuracy was around 74% and loss was around 51%. This is the model is basically saying I'm guessing, but I don't really understand the pattern yet. As training continues, so you can see the whole training is continuing and accuracy is improved to around 81% and the loss has decreased to around 42%. So this tells us that the model is actually learning the patterns in the data. So loss is basically like how wrong the model is. So when loss goes down, predictions are getting closer to the correct answer and mistakes are becoming smaller. Uh, so uh, here you can see actually that after a few epochs, the improvements are becoming very small. So accuracy has stabilized to at around 81% since but like last 12 to 20 epochs, it's almost as 81%. It didn't improve more than 81, which is normal. The model has learned most of the simple patterns it can extract from this data. So in the first epoch that it ran, it just randomly guessed some structure. In the middle one, it has learned some pattern. In the later one, in the last one, it fine-tuned small improvements in weights and bias, and also it has almost finalized the weight at that part. So next step is evaluate this on our test data. So model.fit, the model studied using the training data. Now we need to evaluate our model into the test data. So you remember we actually divided our data into 80% into training data and 20% into the testing data. Um, Now we need to actually test the model is now it's trained. We need to test it in the testing data. So let's testing. Test loss and test accuracy equal to model.evaluate and let's print test accuracy and print test loss. Right. Extreme to scale test. Have we not defined extreme scale data frame? Oh, well, actually data is not data frame, it's only test scale. Right, let's run it. Okay. So before we look into it, let's look into model.evaluate, right? So in fit we were training the model. In evaluate we are evaluating the model against the test data. So you can assume that during model.fit we basically makes the prediction, will calculate the loss, compute the gradients and update the weights. In case of model.evaluate, we make the prediction, calculate the loss, same, calculate the accuracy, but we never update the weight. The weight is whatever we learned from the testing data. We will just use that same weight in the training data as well. So result is that means if we were 100 completely new songs that we give it to the neural network that model had never seen before, it would correctly classify, in our case, 82% of the songs because its accuracy is at 82% and the testing and the loss is 41%. The training and if you see here like our testing and the training accuracies are almost similar. That's actually good, but let's say if it was completely different, during training it's 99 and during testing it's 60, that would mean that the model memorized the training data instead of learning the real pattern. Let's look into another part as well for with TensorFlow. Don't need to generate and code with AI. Let me write prediction model.predict, and let's just look at first 5 songs from the scale dataset. Perfect. So what we are doing here, we are asking our trained neural network to make predictions on 5 songs it has never seen before. So the neural network take each song's features, passes them features. I mean, like you remember all this tempo and genres, sub-genres, and artist popularity, all those features, all the inputs, and we pass them through all the layers that we had created before, and finally through the sigmoid neuron that produces values between 0 and 1. So since we trained our model using this, if you remember, we had like a greater than 50, correct. So we trained it with based on the track popularity, which is more than 50. It means popularity over 50 and skip 0 as under 50. So like either if it's over 50, user is likely gonna listen. If it's less than 50, user is likely gonna skip. So these numbers, they represent the model's estimated probability that the song's popularity is greater than 50. For example, based on everything the neural network has learned during the training, it estimates that the first song that we had provided, there's a 40% chance that this song's popularity belongs to more than 50% category. Likewise, let's say if it's estimated around like 80%, right? It means that it's, according to neural network, there's a 80% chance that the song's popularity will be belong to more than 50. So now here up to us that what level of threshold that we want to define that user is going to listen to the song or not. Okay, previously we told that it's at 50%, but then later we can move it to 80% as well. That let's say if the song's popularity is more than 80 or 85 or 90, then we want user to listen to the song. Then we will basically recommend it to the user. So let's say if we are looking at maybe like thousand songs that we have for user to next look at, and we are pretty sure that some one of the song will have popularity of more than 90%, then we can say that okay, it's our threshold is 90%, or we can just take the top one, right? That whichever has the highest popularity, we want to recommend that song to the user. So it's all based all up to us that which song we want to put in the user's queue. So the whole flow is basically we looked at the evaluate, so how well did the model perform overall. Then we looked at the prediction, that what probability does the model assigns to each new song. Um, and we'll also look at the testing data. We also cleaned up our data set because our data set had bunch of different values. We looked at all the different ways like one hot encoding, then label encoding, transforming the data, dropping the columns. Then we used that the min max scalar to basically put the all the values between 0 and 1 because our data had bunch of different values like tempo is 122, 124. So we to level the field between all the input parameters, we put it into min max scalar to put it to assign all the values between 0 and 1. We slice our training data into 80-20. 80% is used for test training and 20% is used for testing. We also looked into each of the concepts of neural network. For example, what is weight, what is layer, what is neuron itself, then all the sigmoid function, activation function, and then we very briefly we looked into training and testing of the model. So that's it for this video. Thank you.